So hello and welcome to today's webinar, Real-Time Design, Addressing Errors as They Occur. My name is Brittany and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you're unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any issues. Everyone's line is currently muted and will remain so for the duration of the webinar. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly. This webinar will be recorded and posted on the EMA resources page. Once this is posted, we will send everyone who is registered for today's webinar an email with a link to the recording in the next couple of days. That said, I want to thank you all for joining us for today's webinar and introduce you to our presenter, Jerry Long. As Senior Applications Engineer for EMA, Jerry provides high-end customer support for several Cadence products, as well as product development and technical marketing guidance for the timing design of products. With a bachelor's degree in electrical engineering from the University of Texas at Austin, Jerry has been involved in several product lines involving verification and timing analysis. He will start off the webinar with an overview of high-speed design and some common examples, followed by a brief demonstration. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Jerry.
Thank you, Brittany. So hi, everybody. So what we'll talk about today is high-speed design issues and how you can address them in the Cadence printed circuit board tool sets. So usually high-speed circuits, they pose problems that involve your project scheduling. Typically high-speed issues tend to delay things and cause issues that you need to go back and readdress. So therefore they typically affect project schedules and involving late-stage changes. And also that, as a result of all this, your build costs are somewhat hard to manage. So one of the things you need to focus on is when you're dealing with high-speed circuits, how can you control and manage these particular issues? So first of all, let's kind of define the problem. So basically what high-speed means is anytime your path delay for a particular signal is long compared to the rise time of the conducted signal. In other words, when your frequencies and edge rates begin to get fairly high, fairly quick and fast, you're going to have probably some type of high-speed issue come up. Practically every design these days has some aspect of high-speed behavior just because of the interfaces involved for communications and memory storage and things like that. Typically, high-speed problems usually are presented in the terms of signal noise or signal timing. Noise is kind of a broad category. It covers several things like signal quality and EMI effects. Signal timing is a little more specific. There's a lot of things that can affect it, but the bottom line is signals aren't arriving at their destinations when they need to. So just looking at signal noise, noise really is considered anything to be an undesired or non-intended signal characteristic. So as you transmit signals across your board, you typically want to be you want that signal to be received as ones and zeros. So you want a nice clean transmission of the signal, but noise tends to muddy the waters a bit. So you end up getting distortion, you end up getting ringing, or worse, basically just not being able to figure out the content of the signal itself. Noise typically destroys signal quality, and that's mainly it gets to a point where you have a distinct set of data streams that you're transmitting, and normally you can distinguish the 0-1 state changes, but on the receiving end, after the signal quality is somewhat impacted, you're not really sure where those transitions occur. Noise is also characterized as unwanted signal radiation. So a lot of times you'll have EMI radiated off the board, and you need to monitor that and regulate that so that you can control that environment and not affect other circuitry nearby. Timing is more of a kind of a simplistic concept, but it's a complex issue that has a lot of involved factors that affect it. But the bottom line is you're trying to transmit a signal. It needs to arrive at a particular destination at a certain time. The signal has to be stable, and the signal state needs to be recognized. So with regards to timing, there's a lot of issues as well that can be affected in high-speed flows. So when you have these issues, typically the costs that are impacting your design schedules, these days the timing requirements or design requirements rather, you have a lot of time to market demand. So you have a design that's on schedule, you got to get the design done by a certain time so the next stage can take over and get the board laid out. Next you need to get the board built and qualified and tested and then put into a product, and your whole schedule gets to be somewhat complex and very involved. So it's extremely important to find these problems as early as possible to prevent things like increase in manufacturing costs, costly respins, and basically missing time to market schedules. So let's take a closer look at what these high-speed problems and how they present themselves. High-speed issues typically manifest themselves in terms of three subject areas: impedance mismatches, coupling issues, and return path discontinuities. So just taking a look at each one of these individually, with impedance mismatches, you typically get things like signal ringing, things where you get a delay associated with overshoot, undershoot, multiple threshold crossings when you're trying to when your receiver's trying to determine change of states. And they cause reflections, which basically can reduce signal quality. Impedance mismatching can also affect timing in the sense that when a signal has to overcome a specified amount of delay, it's going to impact your timing margin that you have. So as the path continues across the board and through whatever associated paths it needs to make, you accumulate these delays, and it affects the margin at the receiving end, and therefore affects your setup and hold requirements of the receiving device that's trying to read and understand or latch data at the other end. So timing has a basic impact from impedance mismatches as well. So typically, if you know you have impedance mismatches or impedance issues, how do you resolve them? Usually you're trying to locate and move problematic segments of your design trace, of your path traces. Sometimes you need to resize these trace widths, maybe alter stack-up dimensions, so maybe your reference layer dielectric between your conducting layer and your reference layer is too thick, maybe it needs to be thinned out a bit. All of these things typically cost the project early, or basically down the line. So if it's progressed too far, this can be a very costly situation. Looking at coupling issues, coupling is basically just a function of edge speed or the edge rate of a signal and the proximity of traces to one another. So normally you can combat the trace spacing issues with a valid set of constraints in your layout tool, which I'll go into in the demo here in a little bit. But most of the problematic or interesting errors occur in coupling just from the rise and fall rates of your signal transmissions. When they become real fast, they tend to have a high impact in terms of coupling, and most of that coupling is done through layer-to-layer coupling with an aggressor and a victim being impacted, and usually the result is like a crosstalk or induced noise, which basically makes it easier or harder to understand where for the receiving devices to understand where the signal transitions are coming. But not only trace links are affected, sometimes the stack-up can affect coupling issues. So your typical normal stack-up that is not necessarily something where you have odd dielectric thicknesses and whatnot. Typically, if you adhere to normal layout rules and spacing rules, you can control that pretty well. But in some designs require thicker dielectrics or different materials, such that you have more space for the coupling fields to interact with one another. So when your stack-up is part of the problem, sometimes this doesn't look so obvious to diagnose. So in this case, what can you do to help resolve these areas? In the case of trace-to-trace spacing is too narrow, you're going to have to move one of the traces or try to get those trace spacings further apart. Anywhere that there's a parallel routing link that runs parallel for too long of a distance, you need to try to disrupt that parallelism. Maybe there's stack-up characteristics that's promoting this, so you might have to go and alter the stack-up. All of these issues are essentially something that's going to affect your board design, and if it's caught too late in the process, it can be very, very expensive. So you want to try to get this early done, this type of situation diagnosed early in the design cycle. Return path discontinuities are very important to signal quality as well. They can affect trace impedance, because if you don't have a good solid return path for your signal, then there's a lot of delay in the return of the energy back to the source, so that looks like an impedance problem. Signal currents typically use the least path of resistance to return to the source, so normally you're going to see that signal path return usually under the actual conductor itself on the board. So, for instance, you have a ground plane under a signal plane, you're going to see most of that return path basically accumulate underneath that particular trace. But sometimes there's things like split planes or holes in the board, gaps for mechanical things that need to be accommodated for, and that return path can get very complicated. So these things kind of create a path discontinuity, which prevents the easiest effective current flow back to the source. So that's really where most of your return path discontinuities come from. Some of the problems they cause, usually like I said, they affect impedance of the signal trace. So anywhere along the signal conduction, if there's an impedance mismatch, usually that involves, and there's not a reference close, in other words, it's crossing a void or something, usually that involves a radiation effect, because the energy is trying to resolve itself back to a potential back to the source. And if that's not in a convenient distant space, it's going to it basically results in a radiating result of the electronic field and the magnetic field. So this is usually where EMI problems come from, is things like this, where you have impedance mismatches due to void crossing. So solving return path issues usually involves adding more reference places in the most simplest of cases. You can try to put in a reference plane on the other side of your split planes or something. Ideally, you want to really try to move the power and ground planes around to avoid breaks under the signal paths. You want to as continuous a return path as you do a source path. So that's usually what you're trying to resolve in return path discontinuities. Impact of signal timing. Usually there's like I said, when timing is involved, it's basically an issue of a signal not arriving at its destination at the expected time. This is really prevalent in things like DDR designs, where you don't have a whole lot of timing margin to play with. You can look at overall propagation delay, which is basically the total delay from the source to the target along the conducted path for each of the signals. So that's going to have a big effect. But there's also, with the later DDR designs, DDR3, DDR4, there's a lot of relative propagation delay issues associated with those designs. So this means you basically have to keep the data and the clock within a certain amount of distance with each other. Same with the strobe and the clock for latching the data. They have to be arriving within a relative amount of time with respect to each other. So it's very important to navigate total propagation delay and relative propagation delays as you build your boards, and have an idea of a means to manage that, essentially. Phase mismatching can also affect this on differential signals, where you have your complement signal is not exactly in phase with the incident signal. What that typically results in is distortion of the clock crossing threshold, where data is typically latched and timed, and usually causes distortions and therefore major timing issues with there. So here to solve timing issues, what you're looking at trying to control, first of all, you've got to get rid of the impedance issues. Impedance issues are a primary cause of some of the timing problems you run into. So impedance issues are something that you need to make sure you minimize, and then make sure you complete the entire delay tracking path for accumulated delay. So this includes pin delays, which is the delay from the die to the package pin itself, the little wire bond delays. Usually a package that you're using has a particular reference from the vendor of what those particular wire bond delays might be. So you need to account for those, and you need to account for any Z-axis delays. These are via delays in the vertical direction that typically aren't thought about when you look at the delay posed by a particular conductor layer or conductor trace. If your signal path is accumulating several of the z-axis delays, or you have a very thick dielectric where you have fairly tall vias, then z-axis delays can have an impact. And then, of course, you need to resolve your phase issues with any of your differential clocking signals. So how do we look at solutions for these high-speed problems? Well, most people use a rule of thumb, which is a good starting point, but it's no guarantee to find these types of problems early on. You typically have no vision or feedback when you're laying out the board in terms of what if this trace is routed a certain way through a certain pin field or something. What does that do to my impedance? Also, what is my effective coupling when I have a bunch of parallel signals that need routing together? Are they separated far enough, to prevent any kind of coplanar crosstalk or anything like that? Return path referencing, you got to make sure that any of those particular signals have some type of return path as a reference, so it keeps everything in a nice, low impedance type of environment. And of course, signal timing. You've got to have that, be able to know that once you're routing a particular signal, you're not distorting any relative propagation delays, and you need to make sure the overall propagation delay is within requirements. So you typically need a conclusive analysis system during the design cycle. Usually your design cycles have a lot of steps associated with them. So what ends up happening is if you have anything that impacts that particular design cycle early on, if you don't catch it, it can propagate through all the way to the first board being built, and then you'll have to find you find the error, then you have to come back and do a respin, rebuild the board, find the problem, fix it, get another version of the board out. So it's very important for high-speed problems to have some type of management system in place so you can avoid these ripple effects for costly high-speed respin issues. So in this case, with the Cadence toolset, it's a very nice option here and a nice set of parameters to control and manage these. So you can manage these all early in the design cycle with the Cadence toolsets. And typically what this means, you're going to be able to see any violations in real time. So as you're designing, you typically can understand what your impedance values are, typically by constraint feedback and design rules. You can eliminate multiple validation iterations, simply by checks, knowing it's right the first time through. You don't have to go back and recreate it and recreate and try to fix issues. All of this improves your time to market and essentially streamlines your design process. So it's a very effective flow and very powerful tool set to have for the Cadence PCB development arena to be able to monitor all of these high-speed issues with. So what I'm looking at here is I've opened up the Cadence toolset. I'm looking at a board that's a DDR4 design. I've got essentially, if I turn off the etching, you can kind of see with the pin layout, you can see I've got a controller over here on the left side, and I've got two DIMM sockets for memory devices, for my DDR memory devices. So I'm primarily going to be focused in on looking at the signal analysis from the controller over to these memory devices here. So that's kind of my test set, if you will. And so the first thing that you want to utilize here is maybe some of the Cadence visions for impedance and coupling. So just focusing on impedance for a minute, there are a couple of ways to look at visions with impedance. One is without any regard to any kind of boundaries or constraints that you've established in the design. In other words, it just looks at each of the nets or a grouping of selected nets and gives you basically the impedance calculations from the source of that trace to the destination of that trace and gives you essentially a calculated impedance value for that. The other way is through looking at the impedance of the particular trace against a set of constraints established for those particular traces. So I'm going to do the first one without regard to constraints, is basically what's called just impedance workflow vision. So if I come over here to my analysis workflow here, I can set up an impedance workflow simply by selecting the impedance workflow here. And then I have a couple of analysis modes to look at, either net-based or directed group. In this case, I'll set up a net-based first, and then in the coupling case, I'll do a directed group. Both are essentially reporting the same information. One is just a little more focused on a set of signals, maybe a specific interface, if you will. That's the directed group flow. The net-based allows you to, if you want to just throw the whole board at an analysis and see what impedance is everywhere, you can certainly do that with a net-based flow or just a few selected nets. But anyway, in net-based mode, I want to come over and select my nets. Here I get an XNet selection panel. I can filter through the particular signals I have interest in. In this case, I'm looking at basically my controller to DDR signals, which all typically, in this case, start with a PP underscore. So I can basically sort on that or filter on that, select all of those particular signals. And now the tool knows that I have a valid set of nets to analyze, and that's why I get the little green check mark. So the next thing you would want to do is maybe set up some analysis options. Impedance is pretty simple. This particular design has no coplanar traces associated with it, so I don't need to check that, but if you do have such designs, this particular tool flow can accommodate for it. Next thing you want to do is start the analysis. I've already ran this, and just so in the interest of time, I'm just going to load it up the results. And once it's finished, you get this vision of what they call the impedance vision. It's basically a view of the board with regard to impedance. So you'll notice most all of the non-involved nets that I selected that aren't involved in the particular analysis are shadowed out. In other words, they're de-emphasized. And I can kind of focus in on areas of the board where I'm trying to do an impedance analysis. You'll see kind of a scaling here. I can particularly filter this scaling. So for instance, right now, I'm looking at a scale of anywhere from 40 ohms to 69 ohms for impedance of all of those particular traces that I am analyzing between the controller and the memory devices. I can use these sliders here to focus in on, say I want to focus on a certain range. Maybe I can just kind of focus in between 50 and 60 ohms. And then it will isolate those particular signals there and just show you which of the traces come in for a measurement of around 60 ohms, in any of that range. So you can kind of filter out to kind of focus in on selected signals of your choices there. Another way to view this is I can take a look at an impedance table. So if I select this impedance table, what it's going to do is give me a net-based mode, because that's what I've selected here. I can view this table in terms of either single-ended or differential pairs. Right now, I'm just doing differential or single-ended. So my impedance table comes up, and it's basically giving me a rundown of all those signals that I selected in a summary table up top, which is kind of the initial reporting of each particular net. And then a detailed table of each selected net that I have in the summary table shows up down at the bottom. So one of the things I might do is just come up and say, okay, what is the highest violators of my impedance requirements? So in this case, I can sort on the max impedance column of my results. You can also look at impedance length, how much of this particular impedance is affected on the overall trace. And this is in percents. So for instance, I have roughly almost a 70 ohm segment in my clock routing that I might be concerned about, but since it's only 0.5% of the overall length, it's probably might not be an issue. So I can use that as a gauge of whether or not to ignore it. You can also look at overall lengths and delays and some parasitic information on the traces as well. But looking at this, let's go look at address bit 11. That's something that has basically a 3.5% section that's almost 67 ohms. So I can select that. Now my detail table comes up, focused just on that particular trace. I can sort it to find the highest segments here. And then so the segment here with 66.8 ohms up top, I can go and take a look at that. If I want to find in the board where it is, I can just select it with a double click. And then it zooms right into that segment on the layout where that particular area is. So you can kind of see it here. It's this pixelated area right here. Basically, it's a address bit 11. You can kind of see that address bit 11 comes in at somewhat of a wider trace. Then it's kind of neck down, probably to get through a VGA field or something, and then continues on. But basically, this is probably indicative of two problems here with the impedance. One is the neck down, so the impedance changes because the width narrows. And another could be probably, if I switch over and turn on the ground plane and back out a little bit, you can kind of, if I see, I'll turn my shadowing off so you can kind of see where the ground plane is. So here's my ground plane turned on, so you can kind of see this trace for address 11 is within a void. So it's kind of a two-problem situation here. One is a neck down, one is a segment over void. So that's really the reason why this impedance returns at that value. There may not be much you can do about this particular segment, but this indeed illustrates essentially what you might be able to use this particular vision aspect for to identify potential problems here. So another particular situation that you might want to look at with impedance is with the directed groups. So you could switch over and do an analysis with directed groups as well. In this case, what would happen is essentially you would identify the directed groups here. If I go and select directed group and then add basically the group selection that I create. And real quickly, what this does is creates a panel here for you of all the components on the board. So I can come in here and say, show me only components with 100 pins or more, and that's U2, my controller. I can turn off my discretes, so I can identify my DIMM sockets there. And so I want to look at those particular directed groups. Group 1 would be DIMM 1, Group 2 would be from U2 to DIMM 2. So here I can create the group right quick. And then that gives me an idea, or tells the tool basically, that's the set of groupings I want to look at. I'll go ahead and set this out here. And then now I can start the analysis and it'll go off and take a look at that. I have this also already ran, so I can just load that up. Just in the, this runs really fast, but it's usually easier in the middle of a demo here to just bring up the results and show them. So here's the directed group version. So if I look at my table now, it's a little bit less information, but I can switch back and forth between each particular group. So if I look at directed group 1, I see basically a listing of impedance. I'm getting pretty much the same impedance rating as you would expect. It's just formatted in a little bit different grouping. The better thing with the directed groups is you get essentially what's called an impedance plot. So same with coupling. This impedance plot in a directed group mode essentially allows you to look at the details in a little bit of a different fashion. So here I'm looking at all my signals, and I'm looking right now at expanded vision. So what this is a listing of all the nets. The x-axis lists the starting and stopping point of the nets in terms of mils, and then each particular color represents a particular impedance change. So you can see through the expanded that most of the signals are within what I would reasonably say is a 50 ohm range or so, although there are some that are kind of splotchy here and there for segmented issues. You can also look at it in a scatter mode, and this basically gives you more of a relative look at the result. So you can see all this, you're looking at really the same coordinates, impedance on the y-axis, distance from start to finish on the x-axis, but now all of these segment traces are kind of grouped according to color, where the color is essentially the actual impedance that it's looking at. So you can zoom in and do all kinds of control things with it, to kind of come in and look at certain things here. And again, you can also double click on these areas and it'll take you right into the layout where the problematic area is detected. So that's pretty much an impedance vision. Let's switch over to coupling vision and show you the same thing basically with coupling in mind here. Let me go ahead and turn the ground plate off so we kind of get back to where we were. So with coupling, it's the same type of thing. You're basically looking to set up a specific set of nets that it's going to go take a look at. Again, you have net-based or directed group. In this case, I'll just use a directed group. And then again, you want to tell it what is my directed groups. And in this case, I've got still my pin filtering of 100 pins for my controller. And then I want U2. And then on my targeted end, I want DIMM 1 and DIMM 2. So I create that group again. Select OK, and then run my analysis. With coupling, you do have a couple more analysis options. You can come in and again, you can, if your board is such that it has coplanar traces, you can select that and basically detect coplanar trace detection. This particular board was done with a lot of spacing layout constraints already in place, so there's not really any coplanar issues with coupling here because most of that's been taken care of with spacing, careful spacing of each of the traces, so the affected field is not as prevalent there. But you can also have it basically filter out essentially what you want to see. So in this case, a 2% coupling coefficient and a 50 picosecond rise time. These are good default values for typically really good results that you get out of the analysis. The coupling coefficient is basically just what this will set is anything that has a 2% coupling coefficient or higher is the only thing that's reported. Anything below that is not reported. And then the rise time at, like I said, at 50 picoseconds is a really good setting there for just general results. You can also look at a geographic window. So for instance, if you want to make sure that it's looking at aggressor-victim pairs within 10 mils of each other, you can put a 10 mil in here. And then in addition to the overall coupling that it's going to look at, it's going to go out and look for each particular victim to see what's around it within a 10 mil spacing. So you can kind of control that here as well. But once that's set up, again, you would start your analysis. It'll run through the specific analysis. What I'll do is just load up the results again. And again, here's your particular vision once I get those results loaded up. In this case, I ran directed group, so I want to look at my directed group in a worst case mode. Again, I have the coupling plot capability, so I can go and look and see what see what my coupling is just in terms of overall results based on the scaling here of my legend. Again, you can filter out certain things if you want to just focus in on higher coupling coefficients. But in this particular flow, a coupling plot is a little more helpful because you can come in and take a look at where your coupling exists. And so here you can break it down the same way where you have the listing of the nets, the distance from the start to finish, and then the coupling coefficient is represented in color. If I go to scatter mode, I've got a bunch of outliers up here, and this is looking at that mode where I'm looking at everything in just relation of coupling coefficients to each other. So in this case, what you could do, you might want to come in and zoom in this area. I've got a single outlier here that I can go look at. If I take a look at this, it's going to give me a little fly up here. There's the information associated with it. This is address bit 6. It's giving me the information. The victim trace is address 6. The length is 47.3 mils. Distance from the start, how many aggressors it sees, and what that aggressor is and what layer it's on. So I can get some information that way. I can also just double click on this, and it's going to, again, take me to that area on the board where this particular segment is having or experiencing a problem here. So if you can sort of see there's a 6 right there. You can see right in that area there that's red. That's basically the area that this detection of coupling coefficient spiked up. So you can kind of take a look at that, and you can see also that the aggressor here, the aggressor here is one of my on-die termination lines. So you may want to figure out if there's a way to route around that, or maybe the signaling between those two is not fast enough or not often enough to really make a difference. You can also see here, you can see one of the reasons why this was detected is, again, it's a trace that's going over a void. And so it sees much more of a difficult path back to a reference, and so therefore that affects what it's going to try to couple to as a reference. Okay, so that is basic visionality, the basic vision for the tool without regard to any kind of constraints. Let me get this back to normal mode here. Most people have, as they're designing, most designers typically have a set of boundary conditions or a set of constraints that they want to put into the tool initially, and have themselves, as they're laying out the board, have that particular set of guidelines be referenced, so they can see as they're designing whether or not they're in violation of anything. Maybe it's impedance, maybe it's space constraints. So that's the other aspect of visionality here, is you can look at visions overall, like I just showed you, without regard to any kind of constraints, or you can look at visions with constraints. And in that particular aspect, what we could do is first bring up the constraint manager and show you where these constraints exist. And in this case, I put some impedance constraints together here and put into this board. You can see here I'm getting, I want a target of 40 ohms for some of these nets. And basically, I'm getting a lot of violations here. You can see it in the constraint manager in this area. You can also see it if I come over here and turn design rule checks on. Can't really, let me zoom in a little bit in this section, right? If I turn design rule checks on and off, you can see where some of these constraints are detected as you go. You know, that's an area where you can see that. But the visions allow you to take a better look at that overall impedance DRC capability. So if I select my impedance DRC vision, what I want to do, what this allows me to do is basically select an area of nets, and then it's going to basically take those nets, read the impedance, and compare it against the constraints in the constraint manager. And then it's basically going to give you a little more simplistic of a vision, just by showing you what's passing your constraints and what isn't passing. The reds are typically greater than the constraint value, and any blues, I don't see any blues in there, but the blues are typically a smaller impedance result than your constraint value. So we can go ahead and clear that out. Another thing you might that you can accomplish in Constraint Manager is the effect of the ability to, as you're routing, restrict those routes to a certain layer. So typically your stack-ups are set up such that if you maintain a certain routing to a certain layer, it has a consistent access to either a ground plane or a reference. The design rules on that particular layer are set up such that you're going to get a good, consistent impedance result. So you can put in things with what's called layer sets. You can put in things, hold on a second. Had to finish my previous mode there. You can put in things called layer sets, and what that allows you to do is take a route as you're routing. So if I come over here to this particular address line, I want to set it up with a layer set. I can go define what my layer set is. I'll just say my layer set here, just to create a name, and then I can select a couple of layers that are valid to route this on. Any other layer that's not in this list would be an illegal route layer, and so I can set that up, bring it in, and then come back over to Constraint Manager, and then it's going to do an analysis on that and tell me whether or not that particular route maintains connectivity on those layers and nowhere else. So that's what layer sets are all about. That's something that is a good high-speed monitoring tool. In this case, I chose this address line. I don't think it's routed on any of those layers. It's probably routed on the top as well. So that's why it's failing there, because it doesn't meet that. Another thing you can take advantage of here is things like pin delays. Any of the delay segments in the Constraint Manager have the ability to use the pin delays that I mentioned. These are the vendor pin delays associated with the die to package delays internal to the device. So you can turn those on and use them here. You can also go up to the Analyze mode as it does the DRC analysis. You can turn those pin delays on, so any reporting back into either the Constraint Manager or into report files that are generated will include pin delay. Can also include that Z-axis delay, so you can keep track of that as well. So that's some more of the impedance rules that you have at your disposal there. Another thing let's talk a little bit about return paths. So with return paths, what you can do here, since I'm in this area, I'll just switch to return paths. So I can set up a constraint here for return path monitoring for a particular bus. So looking at my address bus, I've got it grouped together. I've got a return path already set up, basically a return path constraint. So what I can do is reference that constraint set, and then it's going to look and apply the reference net, which is the ground net, and try to see where it is in close proximity to all of these particular nets associated with this bus. I've set this up to where it's the ground is the reference net, the closest plane is what it's going to look for. Then it will make that analysis and give me some feedback on results. You can see I got a lot of problems with this particular return path. One of the things that it reports is the maximum violator in each of the lists. I can quickly jump to that. If I select it with a right click, go to source, it's going to jump into the list of where that particular constraint violation is occurring. And then I can double click right here, and that's going to take me right to the place on the board where that return path violation is occurring, and that is address A4. If I zoom back out and turn on my ground plane, you'll see that the reason this has a problem is because there's a void that this particular net is crossing. So what I can essentially do here is come over, select my shove, and then move this particular route out of that void area, and immediately my design rule check goes away. So as I route, I can see these design rule checks come up, and then I can resolve the situation almost immediately there. Another way to look at this is through visions. So if I come back to my vision section, I can look at my return path DRCs. Let me get back to full board here and turn the ground plane off. What I can do here with my return path visions is I can come in and just select an area of interest, and then it's going to go make that analysis. And then now I can just zoom in right in this area. These are the return paths, basically all the signals that have return path issues. The one I just fixed was right in here, but you can see that void being present right there. It's also causing that particular return path issue. And then there's some voids over here. If I turn the ground back on, you can sort of see that if I turn that off. But all of this area has voids in my BGA pin field here. So all of those voids are presenting issues as well. So visions are a good, powerful feature for the tools to allow you to catch these particular high-speed problems early on in the design cycle. So let's go ahead and get back out. I'm going to turn my ground plane off again. Another thing that you can take a look at through here is basically how stitching vias are affected in your return path. So that's something that's new. If I come back over to my constraint manager, it's right here. I can come in and look at a particular return path section here. Stitching via distance is where you've got a particular set of vias that are crossing maybe a particular set of layers, and you need to have these particular paths. Let me, still in mode that I haven't finished. You can set up to where if you have stitching vias in place, you can set up and have the tool monitor to make sure that those stitching vias are close enough. And in this case, I've got a couple of stitching vias set up for this guy right here. So what I can do is set that up as a reference path to the ground plane, have it reference to the closest plane, and then put in a parameter that it's going to take and measure. And now it'll come in and make that measurement, and I can see now that I have maybe a stitching via problem there. Again, I can just double click on this signal. It takes me over to that area on the board where there's my stitching via problem. Here's my two stitching vias. One is out of place. So this particular via right here, turn my vias on. I can select this and move it back over and get it somewhere close in the vicinity. And then as soon as I get it close enough, according to my constraints, my warning goes away. My DRC is affected. So you can see these constraints pop up as you design, and you know, you're effectively notified almost immediately as the particular problem happens. Lastly, with regard to timing, I'm going to turn off everything and just focus on the data bus, which is this layer here. So if I come in here, I've got a DQS strobe here. So as I route with regards to phasing and pin delay and things like that, if I look at my constraint editor or my constraint manager, if I look over in electrical under differential pair, I can set up static phase and dynamic phase constraints. So basically what this does is monitor all my differential bus routing and allows me to keep track of that to make sure that that differential bus stays in phase. In other words, the delay for each segment of that bus is the same. So in this case, I've got some static phase set up. What I can do here, and pay attention to this lower right corner, because as I begin to alter this this particular bus, you'll see basically a heads-up display come up and show me how I'm affecting, what I'm doing with the route is affecting my phase. So to make sure I'm not in any kind of mode. So what I'm going to do is go into a delay mode, so I can add delay in here, and you see that heads-up display come up, and I get a static phase reading where I'm really altering the static phase. So I'm you know, destroying the phase relationship between it, and I'm also destroying the relative delay there, the relative delay constraint that's also on this signal. So as I begin to alter that, you can see how it affects it. You can also see this same effect as you're routing. So as you know, if this was a routed effect where I haven't routed it yet, but I'm in the process of routing it, you would see that heads-up display come up and allow you essentially some phase differences. Okay, so that's about all I have to show you today. Just to sum this up, basically, Cadence toolsets provide you with the vision approaches and some of the constraint-driven design analysis with the heads-up display for phase and the impedance and things like that. It allows you to basically catch these high-speed issues early on in your design process and avoid costly design respins and keep your time to market reasonable and your cost down. So with that, I'm going to hand it back to Brittany.
At this time, I would like to open up the floor for the Q&A. Please enter any questions you have in the chat now. If we're unable to address your question immediately, we will be in contact with you. We only have a few minutes left here for some questions, so we'll get started. First question I have for you, Jerry, is can coupling vision identify coupling in the z-axis, for example, two nuts on different layers?
Yes, that's just about what it focuses on is layer-to-layer coupling. That switching that I mentioned there, where you can actually have it detect coplanar coupling and coplanar impedance, that takes care of the coplanar in addition to the z-axis coupling. So yeah, by default, it's essentially layer-to-layer coupling involved.
Good to know. And would the program typically flag impedance mismatch of signals crossing split grounds, and would it take into account stitching caps?
Yes, it does. So as soon as you cross a void, basically if you have impedance constraints set up, when you cross that void, you should see some type of reflection regarding how that void crossing is affecting the impedance value there. What was the secondary question on that?
Would it take into account stitching caps?
It'll take into account the stitching. It doesn't take into account the actual component. It takes into account the pad and the connectivity of that pad. So if that pad is basically connected to ground, then yeah, that is a reference point. If it's on this in proximity to the particular trace, it'll use that as a reference point. Yes.
And we have somebody who is wondering how long did the impedance workflow take in the example and on what computer?
It runs really fast. I didn't do it here just because I was showing so many different flows, but this particular flow that I did with all of the signals from the controller to the memory devices, that runs and completes in about 7 to 8 seconds. So, you know, that was about 100 signals. On this particular relatively complex board. I think this has roughly 10 or 12 layers. So yeah, it was able to do that analysis in about 7 to 8 to 10 seconds around in there. So it's very fast. It's not anywhere near what you typically see signal integrity simulations take.
All right, and thank you, Jerry. Looks like we have a bunch of questions still coming in. Unfortunately, we're out of time for today. However, if anyone has questions that were not addressed during the webinar, we will be following up with you on an individual basis. I'll be closing the webinar now, and we'll be sending everyone a recorded version of today's session with the slide deck within the next few days. Thank you for taking the time to join us, and enjoy the rest of your day.